of ions in the atmosphere of the sun, and they're not at rest, they're moving about. So this electric field is changing like crazy, and that electric field would have a time component. Okay, now that becomes too complicated. Okay. Right now we don't want to worry about that, so we nail these guys down. For this electric field, it turns out that you don't need three functions, all you need is this one function, and that's the message.
And it's important that they're not moving because that create magnetic fields as well.
Yeah, and we don't want this time dependence.
That's why you always say like electrostatic.
That's right. So we give it names, but there's a whole bunch of stuff hidden behind it. Yeah. All right, so what does this equation say? This is the punchline. The gradient operator tells you what direction does V increase the fastest, and the electric field is pointing in the opposite direction. Okay? So if you have an electric potential and the potential is increasing the fastest in this direction, the electric field is pointing in that direction. Okay? And so let's go back to our diagram here. Remember, potential energy for this guy was high here, potential energy was low. But we defined something called electric potential, that is high here, that is low here. Electric potential is increasing in that direction, and the electric field is pointing in the opposite direction. Okay, and that was that equation. That is the whole chapter. Okay, I'll pause now. Do you guys have any questions? Because when we go into the slides, it won't even look like this. Because nobody wants to introduce the gradient operator and all that kind of stuff, and so we have to hide it in all kinds of stuff. All right, what's your question, my friend?
I take it back.
You take it back.
Change my mind.
Change your mind. All right. Anybody else? All right. So electric potential is denoted by V. Electric potential energy is denoted by U. This is measured in joules. This will be measured in volts. And as you guys know, remember that all units are named after scientists. Okay, so Mr. Volt worked in this field. Okay. Again, here the Maxwell's equations, causes, effects. Okay. Everything we study. So charges produce electric fields, and to detect electric fields, you need charges. This is the Lorentz force equation. Moving charges produce magnetic fields, and to detect a magnetic field, you need moving charges. So there's a beautiful symmetry in there. Okay, so what this diagram is showing is, this is the gravitational field. So this is the acceleration due to gravity is a vector field. What is the acceleration due to gravity in this room? 9.8 meters per second squared. You're telling me the magnitude of this vector. Which direction is this vector pointing? It's pointing toward the center of the earth. Is this vector pointing the same? Is that parallel to that? No. Right? Okay. So, and as you go higher and higher, the magnitude of this vector will get smaller. So if it's 10 meters per second square here, if you go, the radius of the earth is 4,000 miles. So if you go 4,000 miles above ground, what will the magnitude of this be? A quarter. Very good. Good. 2.5 meters per second square. All right, in a gravitational field, you don't have a positive mass and a negative mass. Mass only falls in one direction. Okay? In an electric field, you have a positive charge and a negative charge. A positive charge falls this way, a negative charge falls that way. Okay? So, with respect to mass, all you had to do was define potential energy. But because you have two kinds of charges, it turns out that you have to define potential energy and electric potential. And this is potential energy per unit charge. So this is a quantity that is the same at a given location, independent of the charge. This guy depends on the location, but it also depends on the charge. Okay? So the way the two are related are change in electric potential is change in potential energy divided by Q. Okay? The reason we had to define this was because we had two different kinds of charges. Okay. Whenever we have whenever you hear the term potential energy, that means the force, underlying force, is conservative. What does that mean? When a force is conservative, what does that mean?
You can't lose energy in a enclosed system.
It's no heat, nothing lost to thermal energy, right? No friction?
Friction is not a conservative force. What a conservative force means, okay, so the work done by that force when you go along a closed path, so let's say if you grab hold of a marble and take it around in a circle, you're applying a force as well, but the work done by gravity on this marble is zero. That's what a conservative force means. The work done by a force is independent of the path. If you take a marble from here to there, gravity does zero work. I mean, the work done by gravity in going from here to there is the same as in along this path, or along this path, along that path. Okay. So conservative force means conservative force. And so corollary is work done on a closed path is zero. Okay. Well, in practice, what does this mean? We've seen this before. You guys all remember this. All I need to do is remind you of this and it'll all come back. You've seen this in chapter 1. So let's say here's a slide that's frictionless, and you drop a marble from there, and it's going at a certain speed. Now I'll design another slide. What speed is it going at on this slide? Same speed. Okay, that's what conservative gravity, if gravity is that's what we mean by conservative force. Okay, the work done by gravity is the same along those two paths. Okay, so for it to go at the same speed, of course, friction needs to be absent. Okay. All right, so work done by gravity is independent of the path, and that's a conservative force. All right, so work done by a force in going from initial to final path is this line integral. Okay, I'll be back in a second.